Hey guys, this is the lesson for section 6.6 in the Nelson textbook, operations with algebraic vectors in 2 dimensions. What we have here is we're talking about doing the same operations as we had with geometric vectors, now with algebraic vectors. So for the warm-up here, we have a question that says consider the following 2 algebraic vectors, OP and OQ, draw them on the Cartesian plane and try to add them to find OP plus OQ. How do you think this would work? So right now, I'd advise you just pause the presentation and just try that on your own for a couple minutes and see if you can even, on your own, figure out how this might work. Okay, hopefully you were able to come up with something on your own. Right, at least you were able to draw those 2 vectors. So first of all, let's draw those 2 vectors here. Okay, so there are the vectors OP plus OQ. Now, what we can do is we can slide the vector OQ into position so that we can then add OP plus OQ. So we'll do that. Okay, so there it is. And now we'll just draw the resultant when we add those 2 vectors together, which will look like that. And that is OP plus OQ. OP plus OQ. Now, just by looking at the coordinates of the tail of OQ, pardon me, of OP plus OQ, we can see that those coordinates are actually four, 5. Right, so just by even drawing it, seeing where the tail of OP plus OQ falls, we can see, well, that vector must then be 4, 5. So hopefully you were able to do something like that, or at least get part of the way there when you tried it on your own. All right, now what I'd like you to try is actually do that same question, but use the unit vectors I and j, like we talked about yesterday, and draw a picture now by moving in the unit vector directions I and j in the horizontal and vertical directions, and then see if we can't do that as well. All right, so let's draw those same vectors again, and this time we'll draw the I and j components in there, and I'll show you what I mean. So we can draw the vector OP once again, like so, and now what we can do is draw those unit vectors I and j in there. So for example, we're going to move one vector I, or 1I to the right, and then 3 j's, which is the unit vector going in the vertical direction. So j, j, and j. So then we can say that the vector OP is 1I plus 3j. Like so. And then what we can do is draw the vector OQ beginning at the tip of OP, so it's in the correct position to make that addition. So let's do that as well. And there's that vector, and notice this time we can do the same thing and say, well, we can do the i's and the j's. So 3 i's and 2 j's in this case. So now it's just a matter of counting the i's and j's to get from O to the tip of OP plus OQ. And again, remember that the vector OP plus OQ will be drawn from the tail of OP to the tip of OQ, just like last time. So it's going to look something like this. And if we count the i's and j's now, you can see that we're just going to go 1, 2, 3, 4 i's, and 1, 2, 3, 4, 5 j's. So now if we also write OQ in terms of I and j, 3i plus 2j, and then write that addition statement, which is OP plus OQ is I plus 3j plus 3i plus 2j. If we then make that addition by adding the i's and j's together, and because we know that vector addition is associative from the other day's work, we can just simply say that we have I plus 3i is 4i, and 3j plus 2j is 5j, and therefore the vector is 4i's and 5j's, just like we counted on the diagram, or on the picture. So as you can see here, I have this written in general, right? So in general for vectors OB and OA, with a vector A being AB and vector B being CD, you can see both in component form and coordinate form how to represent the vector OA plus OB. So just take a second to make sure you have that down in general. Pause the video if you need to. So now let's take a look at scalar multiplication. So if we consider the vector OP 1, 3 again, what would the vector 2OP look like? So first of all, let's draw OP once again. And if we're going to take two OPs, it's just like that, right? We need two vector OPs that we're going to add together. So let's draw another OP starting at the tip of the original OP. So let's do that. And then notice just simply the coordinates of the tip of the second OP. When we take the two OPs together, we then get coordinates of 2, 6. And just note that if we did 2 times the vector OP, that's 2 times the vector 1, 3, that it does just look like we multiply each of those coordinates by 2. And then we're going to get the new tip of OP. Now what would happen if the scalar we're multiplying it by is negative? So there is OP once again. So now we're going to draw 3 OPs, but in the opposite direction. So 3 OPs in the opposite direction. Now, due to my lack of foresight, it doesn't quite fit on the graph, but what you'll notice is that the coordinates of that endpoint are just what we'd expect them to be. If we took -3, the scalar -3, and multiplied it by the vector OP, that is -3 times a 1, 3. So from the diagram, you see that it's reasonable to see that the new coordinates of the tip of that vector -3 OP are -3, -9. So yeah, it does just look like we multiply each of the coordinates by whatever scalar is there. So here I've written out this scalar multiplication of the Cartesian vectors in general, right? So in each case you can see that we're multiplying the vector OA by the scalar m. On the diagram you can see here that the vector OA is in black and MOA is in red, and that's if m is greater than 0, and it's in green if it's less than 0, meaning we're going to get a vector in the opposite direction multiplied by the absolute value of that scalar m. So notice that all the vectors are collinear. We talked about that if you multiply a vector by a scalar, you will get a collinear vector, or two vectors that lie on the same line. And notice over here, because of the distributive property, we know that we can multiply m times each of those vectors because scalar multiplication distributes over vector addition, which shows that in general we're going to get either one of those cases. Now, one thing that we're going to want to be able to do is write a vector, or the position vector, that goes between 2 points. And remember, position vectors always start from the origin. So if we have a vector that starts at a point other than the origin and goes to a point other than the origin, we want to be able to write it as a vector starting at the origin, because again, remember, position doesn't matter, we can move it anywhere we want. So if we have a point A, 1, -3, and a point B, -2, 2, then what is the vector AB? So the first thing we're going to do here is draw or plot the points A and B. So let's do that. So there I've drawn the points A and B and also the vector AB, which goes from point A to point B. Now, really what we want to do is talk about if we were to draw that vector starting at the origin, what would the coordinates of that tip be? So we're going to look at that just like we would using the same concept as slope. Meaning if I start at A, how far do I have to go horizontally and how far do I have to go vertically to get to B? And if you remember from grade 9, we'd call the direction we have to go, or the distance we have to go horizontally, delta x, and the distance we have to go vertically, delta y. Right? So what we do is say, well, delta x in this case, or the distance we have to go horizontally, is going to be the difference in the x coordinates. Right? So because we're doing vector AB, we're going to go B minus A. So that would be, delta x would be -2 minus 1 or -3. And then delta y, because we're going from B to A again, we're going to go 2 minus -3, which gives us 5. So now if we were to draw a vector with the same direction and magnitude as AB, but this time make it a position vector, meaning it's going to start at the origin, our vector would start at the origin, and then its terminal point or its tip would be at -3, 5. So -3, 5. So we can then draw that vector, and it would look like this. So then the vector that we would call AB would be the vector -3, 5. Because again, when we're listing vectors on a Cartesian plane, we always want them to be position vectors, meaning starting at the origin and ending at that terminal point. So that's going to be then the vector AB. And we'll just show how we got it as well, right? We said the vector AB is, the x-coordinate is -2 minus 1. And the y-coordinate was -2, or pardon me, 2 minus -3, right? For the final point of -3, 5. So that was the terminal point, which means that is our vector AB. So if we wanted to talk about this in general, right, in general, for 2 points, we'll say A, x1, y1, so that's the first point, and B, x2, y2. The vector AB, and remember direction matters here, right? The vector AB is not the same as BA, so it does matter which order that we're going to subtract the coordinates in, so that's going to be x2 minus x1, y2 minus y1. So in general, that's what it looks like. So now we can look at an example like this, and again, this is like the simplifying of scalar multiples of vectors, or writing scalar multiples of different vectors as one vector. So again, because we have shown the properties of vector addition as being commutative and associative and distributive over scalar multiplication, right, we can now go ahead and simplify something like this. And again, you might say, well, we have two ordered pairs there. How do you know they're not points? Right? Again, you look to the context of the question, and it says write a vector equivalent to the following. So because it mentions vectors here, the context indicates that those ordered pairs are in fact vectors and not just points. So when we go to simplify this, We saw earlier that if you're multiplying a vector in Cartesian form or as an ordered pair by a scalar, we're just multiplying each of the x and y coordinates by that scalar. So we can multiply both 4 and negative 9 by that vector, or by that scalar 3. And we can multiply the vector 1, 0 by that scalar multiple of 2. Now it is negative 2, and there's two ways you could approach it. You could either say, well, we're still going to subtract and multiply each of those coordinates by 2, or you could say it's equal to, again, the 12 negative 27, but this time instead of multiplying it by the scalar of 2, the second vector, we're going to multiply it by negative 2, which means it's going to change to addition here. So we're either adding the vector negative 2, 0 or subtracting the vector 2, 0. Because they're opposite vectors of each other, that makes sense, right? Adding the opposite. Either one of those will give you the same answer. So if we did the first one, as we saw earlier, when we're subtracting or adding vectors in Cartesian form, we simply add or subtract their x coordinates and y coordinates. So this will give us the vector 12 minus 2, comma negative 27 minus 0, or the vector 10 negative 27. And again, just to note, if we did do it the other way, we get 12 plus negative 2, or 10, and negative 27 minus plus 0, pardon me, or negative 27. We get the same thing. So simplifying vectors in Cartesian form involving scalar multiplication and addition subtraction here, that's how it would look. And that's all because we have done this, we've shown these things earlier in the lesson. So now if we're asked to find the magnitude of the vector in the previous question, again that vector was 10, negative 27, remembering that you don't have to really memorize that formula or the length formula from grade 10, the length of a line segment. Remember, it's just Pythagorean theorem, right? So that if we look and say, well, really, we can make a right angle triangle here, like so. And note that in terms of distances or magnitudes here, the magnitude of this line is 10 and the magnitude of this line is 27. So the magnitude of our vector, and just for reference sake here, we'll call this vector the position vector OP. This then, the blue vector, the magnitude would be the length of that vector, right? So that's the magnitude of OP. So then using the Pythagorean theorem, we know that the magnitude of OP squared is equal to, in this case, 10 squared plus negative 27 squared, right? Now, we could even consider the fact that that's negative 27. I mean, it doesn't make sense in terms of the length of the triangle, but it does make sense in terms of the distance that you travel to get there. Whether it's negative or positive, you're going to get the same answer again because you're squaring that, right? So the magnitude of OP squared is going to be 100 and then plus 729. So the magnitude of OP squared is just 829. And again, by taking the square root of both sides, we get the magnitude of OP is the square root of 829, or the magnitude of OP is 28.79. Now remember, normally when you're taking the square root of both sides of an equation, recognizing that square roots can be negative or positive, right? But in this case, because we're dealing with a magnitude, we're considering just the positive, right? Because magnitudes indicate a positive value. So that's it for this lesson. Again, the setup of the lesson similar to the last one, is a little more involved in the actual application. The actual application of the scalar multiplication and the addition subtraction of Cartesian vectors is pretty intuitive, and it's what you'd expect it to be. But again, we've shown that ahead of time. So really today, coming out of this, can you add or subtract two algebraic vectors using both ordered pair and unit vector notation? Can you multiply an algebraic vector by a scalar in both ordered pair and unit vector notation? And can you find the magnitude of an algebraic vector? All right, so those are the questions that you can ask yourself to make sure that you know that you're successful in the material that we talked about. And for those of you who are actually in my class watching this, here's the homework that you can work on tonight. Again, please come prepared next class with any questions that you have. All right, good luck, guys.